Okay, good morning, everyone, and welcome to the last lecture for Physics 660. So we've been talking about the Clebsch-Gordon coefficients that occur when you combine two angular momenta with quantum numbers J1 and J2. Okay, and one way of writing these is in this way, as the matrix element between the product basis states and the total angular momentum basis states. And last time we worked out, or we sketched out an algorithm to compute these things. And so today I'd like to concentrate on the properties that the Clebsch-Gordon coefficients satisfy, starting with the properties that we've already used in the algorithm, and then talking about some new ones. So most of what I'm going to say we've already seen in examples, but there will actually be a couple of new ones too. So first of all, there are recursion relations. So the Clebsch-Gordon coefficients satisfy recursion relations of two types. One that we used, and the one we used you can write in the following way. I take square root of j times j plus 1 minus m times m minus 1, that multiplied by a Clebsch-Gordon coefficient where the m value is down by 1 from whatever we started with. And that can be written as a sum of two terms, both of them involving square roots. One of them looks like this. Okay, where now I multiply by a different recursion, a different Clebsch-Gordon coefficient, which has m1 increased by 1 and everything else the same. And then there's a second term, which looks like this, j2 plus 1. So basically it's the same thing, but with the label 1 replaced by 2. Okay, and I'm using colons to distinguish the product basis. Okay, and so that's in disguise the thing that we used that came from the J minus operator. By the way, there's a different way of writing the things under the square root. So for variety, one could write that thing under the square root. It turns out it factors into j plus m times j minus m plus 1. Okay, so it turns out there are two different ways of writing the thing under the square root that are of roughly equal complexity. So there's no particular reason to favor one or the other, and they don't, at least to me, they don't look immediately obvious that they're equal, but they are. And so then you could do the same thing to rewrite these things under the square root by factoring. Okay, but in any case, these come, so this one comes from acting with the operator J minus for the total angular momentum state, which is J1 minus plus J2 minus. So that's one recursion relation, and then there's a different one that we didn't use because we didn't need it to do our algorithm. But we could have instead organized the whole algorithm around this one. Okay, and so M1, M2, and now instead of lowering the M value, we're going to raise the M value. Okay, and on the right-hand side, there's J1, J1 plus 1, minus M1, M1 minus 1, because now on the right-hand side, for the M1 and M2 values, we're going to lower them. Oops, that should be a colon. Okay, and then there's another term, J2 instead of J1 gets changed. And so it looks like this. Okay, and this would come about from looking at the J2 operator, the J plus operator acting on these states. And then that gives you an identity, which you can rewrite in terms of these recursion relations. So these recursion relations just involve the Clebsch-Gordon coefficients and these horrible, ugly square roots. Okay, so in addition to the recursion relations, there are orthonormality conditions. And there are two of those also. So what these really come from is orthonormality of the basis states expressed in terms of Clebsch-Gordon coefficients. So the first one looks like this. You sum over all the possible values of M1, and M1 can be as small as negative J1 and as large as J1. You do the same thing for M2 over all of its possible values. And then you put in the Clebsch-Gordon coefficients. And remember, these things are always real. So when I write it in bracket language reversed from the way it's defined, and nothing changes, because that would just take the complex conjugate. And so what I'm doing here is I'm taking the Clebsch-Gordon coefficient of sets of Clebsch-Gordon coefficients with different J and M total angular quantum numbers. Okay, and then this turns out to be delta J, J prime, delta M, M prime. So it's one if and only if J and J prime are the same and M and M prime are the same. And so the reason this is an orthogonality condition is if I just look at this part of it, where I'm summing over those things, by completeness, I've put in a sum over a complete set of states. That makes it the identity operator. And so now if I were to take that identity operator and cross it out, then what's left here is just the orthonormality condition for the basis states in the total angular momentum basis. Okay, so then you can do a different orthonormality condition where instead of summing over M1 and M2, now I'm going to sum over J and M over all possible values that they can take, though. So for J, it can be as small as the absolute value of J1 minus J2, and it can be as large as J1 plus J2. And then for each of those J's, the M value can be as small as negative J and as large as J. And so really what I'm doing here is, again, putting in a complete set of states. But now between different product basis states. So I have M1, M2, and then over here I'm going to write M1 prime, M2 prime, which could be different. Okay, and the statement is you get 0 for this unless they're the same. So this is delta M1, M1 prime times delta M2, M2 prime. Okay, and once again, we can see this just from the fact that all we've done is put in the identity operator by completeness. So the sum over this complete set of states is the identity operator, and then what's left over is just the orthonormality condition with these two states. Okay, so we have recursion relations and orthonormality conditions. And if you look at our algorithm, what our algorithm amounted to was just using these ones and these ones. And then the other recursion relation and the other orthonormality condition give you checks. So if you wanted to, you could take your computer running Mathematica and teach it each of these 4 sets of conditions, and then just say, okay, here's a bunch of unknown Clebsch-Gordon coefficients that I want to know the values for. Go solve these equations. And when it does, it will actually solve the equations, and then it will find that some of them are redundant. Many of them are redundant, actually. And those will be checks that no mistake has occurred. But being a computer, if you typed everything in correctly, no mistake will occur. Okay. So there are some other conditions on the Clebsch-Gordon coefficients that we can write down, some of which we've seen before in action. So one is called the triangle rule. Okay, and the triangle rule just tells you that it's a condition that tells you when the Clebsch-Gordon can be non-zero. And it says the Clebsch-Gordon can be non-zero only if there's a triangle. And the triangle is a triangle that has sides J1, J2, and J. So that's just rewriting the fact that J1 minus J2 in absolute value has to be less than or equal to J, has to be less than or equal to J1 plus J2. That's the same condition as saying that they can form the sides of a triangle if you want. Okay, but the trivial triangle is allowed. By the trivial triangle, I just mean the situation where the triangle has 0 area. So if that were, so I could have this be J1, and this be J, and this one be J2. That's a triangle that's sort of degenerate because it has no area because they're all in a line. But that's an example of a trivial triangle, so it's allowed, and you get a non-zero Clebsch-Gordon coefficient. Okay, the second condition is that it's non-zero only if m is equal to m1 plus m2. Otherwise, the Clebsch-Gordon coefficient will be 0. And really, all that amounts to is, so to prove that, all you need to know is that J sub z is equal to J1z plus J2z. So it's pretty easy to prove these things. Okay, the third thing is something you can't really prove. It's more of an assumption. It's the Condon-Shortley convention for the Clebsch-Gordon coefficients that we've been using in our algorithm. And so one thing that says is that all the Clebsch-Gordon coefficients are always real. Okay, and if you want to think about why are we allowed to know that they're always real, what it really amounts to is that you go back to these conditions and all these square roots are real numbers. So if all the coefficients are real numbers, then all the things that you're going to solve for by solving these linear equations are going to end up being real numbers as well. Okay, so that just tells you can pick them always real, and so we do in the Condon-Shortley convention, but also we can choose some of them to be positive, and this amounts to saying that they're positive when m equals j. Okay, in other words, when m is the largest possible value it can be, that's sort of the first one we encounter in our algorithm. We choose that to be positive, and then anything else, its sign is going to be determined by that. So here's a maybe slightly less obvious consequence of that, is what happens if you flip the sign of each one of the m's. So if you take a Clebsch-Gordon coefficient and you flip the sign of all the m's, you get another non-zero Clebsch-Gordon coefficient. And in fact, here's a formula for it. Okay, if I write the first one, it's -1 to the j1 plus j2 minus j, which is always an integer, even if j1 and j2 are half integers. And this is minus m1 minus m2 j minus m. Okay, so that's another check that you can do, because you can independently compute this one and this one starting from the algorithm, and then if you haven't made a mistake, they should be equal up to a sign, which you can figure out from what the j's are. All right, so a nice thing to do sometimes is to look at what happens if j1 and j2 are actually the same. So addition of same, j1 equals j2. And now I'm going to call j1 and j2, I'm going to call that equal to capital J, just to give it a name. And so now if I do the tensor product in the product basis of, oops, I should have called that, yeah, that's capital J. Then I get, the largest thing I can get is 2 capital J. The next largest thing I can get is 2 capital J minus 1. The next largest thing is 2 capital J minus 2, and I keep going until I get to 1, and then finally 0. So they're all integers on the right. Integer angular momenta, even if capital J was, say, 1/2. And a nice thing is that you can assign symmetry labels to these as follows. The highest one is always symmetric. The next one is always anti-symmetric, and then they alternate. And so I can't tell you what 1 and 0 are because I don't know where it's going to end up when I alternate. But these symmetry labels are telling you what happens when you exchange the 2 angular momenta that you started with. So symmetry labels S for symmetric and A for anti-symmetric. They govern the exchange of the 2 angular momenta. Okay, and the rule is the highest one, the highest angular momenta is always symmetric. And after that, they alternate. Okay, so one example of this that we've already seen is what happens if you do a spin 1/2 and another spin 1/2. So if I take their tensor product, the result is I get a angular momentum 1, which is symmetric under the interchange, plus an angular momentum 0, which is anti-symmetric under the interchange. That's what the general rule tells us. And we've all seen this already, because here are all the symmetric ones. So in the total angular momentum basis, the state 1, 1 was equal to up arrow. And the state 1, 0 was 1 over square root of 2 up arrow, down arrow, plus down arrow, up arrow. And the state 1 minus 1 in the product basis was down arrow, down arrow. And so now the point is, if I interchange a spin up with a spin up, oops, okay, then since they're the same, nothing happens. Here I'm interchanging this one with that one, which turns it into up arrow, down arrow turns into down arrow, up arrow, and vice versa. So the fact that there's a plus sign there between these makes this a symmetric thing. And then the same thing for the down arrow, because they're the same thing, when I interchange them, I get the same thing back. And so those are all symmetric. And then there's the all anti-symmetric case, which is the spin 0. There's only one state like that, but that's, remember, 1 over square root of 2, up arrow, down arrow, minus down arrow, up arrow. Okay, and so if I start with this state and I interchange those two spins, then I'm just changing up arrow, down arrow into down arrow, up arrow. And now it's anti-symmetric because I get a minus sign when I do that. Okay, so that's an example that we were already familiar with. A more trivial example is I could take spin 0, tensor product spin 0. And of course, then what I'm going to get is total angular momentum 0. And it's symmetric because when I exchange things that aren't there, I get back the same thing. When I say things that aren't there, I mean there's no angular momentum, direction, or eigenvalue to exchange. So that was too trivial. Now we can do, for example, spin 1, tensor product spin 1, or just any angular momentum across the same angular momentum. And the rule tells us this is going to be spin 2, or angular momentum 2, symmetrically, plus 1 anti-symmetrically, plus 0 symmetrically. Okay, and so to see examples of that, so an example of the basis states with 2 symmetric are, for example, there's the total angular momentum state 2, 2, which in the product basis is just when they're both aligned to be plus 1. Okay, so if I interchange 1 and 1, I get back the same thing. There's the fact that if I take 2, 1, if you work out the Clebsch-Gordon coefficients, this turns out to be, it looks similar to the 2 spin case. And that's because it has to be symmetric. Okay, and then maybe slightly less trivial, if I do 2, 0, this turns out to be 1 over the square root of 6 times, in the product basis, 1 minus 1 plus 4 times 0, 0 plus minus 1, 1. Okay, and so now if I interchange the 2 angular momenta, this doesn't change because they have the same m values. And this one turns into this one, right? Because they have a plus sign in front of both of them, and they have their m values exchanged. So then you can do examples of the 1 anti-symmetric combination. So they have total angular momentum 1, and then m value 1, and it turns out this is 1 over square root of 2, 1, 0, minus 0, 1. The minus sign is there because when we interchange the m values, we have to get back the same thing anti-symmetrically. So it has to be the opposite sign. And then the 1, 0 state, oops, turns out to be 1 over the square root of 2, 1 minus 1 minus 1, 1. Okay, and then finally for the 0s combination, I don't have to say example because there's only one of those states, and so it's 0, 0. In the product basis, that turns out to be 1 over the square root of 3, 1 minus 1 minus 0, 0 plus minus 1, 1. And again, that's symmetric. Don't be fooled by the minus sign here because when I interchange the two things, I get back the same state. And when I interchange these two, that turns it into this. And notice they have the same coefficient in front, namely plus 1 times 1 over square root of 3. Okay, and then for even more complicated things, if I take a angular momentum 3/2 state and I tensor product with another angular momentum 3/2 state, I get the following combinations. There's an angular momentum 3 state, which is symmetric, angular momentum 2 state that's anti-symmetric, angular momentum 1 state that's symmetric, and angular momentum 0 state that's anti-symmetric. Okay, and just to show off what these look like, if you look them up in the Clebsch-Gordon tables that you can find on the internet. So an example of the 3S, 3 symmetric, is that total angular momentum 3 with m value 0 happens to be 1 over the square root of 20 times 3/2 minus 3/2 plus minus 3/2 3/2. So when I interchange those two terms just change into each other. And then plus 3, 1/2 minus 1/2 plus 3 minus 1/2 1/2. So again, those two terms just change into each other when I interchange the m values. Okay, an example of the 0s or 0 anti-symmetric basis states. Well, actually, there's only one of them, 0, 0, and it turns out to be 1/2. That's the Clebsch-Gordon times the same actual basis states, but now with minus signs to make this thing be anti-symmetric. Okay, and this turns out to be minus 1/2 minus 1/2, and then plus minus 1/2 1/2. So again, this is very useful, not just for checking what happens, checking that you've done the Clebsch-Gordon coefficients correctly, but also it turns out if you have identical particles, which we'll talk about in just a few minutes. Okay, any questions on this so far? Okay, so one thing I want to emphasize is that this assignment of symmetric or anti-symmetric only works if the two angular momenta are the same. So you can't assign symmetric or anti-symmetric labels to the product basis states if J1 and J2 are not the same, as we were just assuming. Okay, and the reason for that is just if they're not the same, you don't know what it means to interchange them. So for example, if I have one tensor product angular momentum 3/2, then you're going to get out 5/2 and 3/2 and 1/2. But there's no way to put a symmetric or anti-symmetric label on those different product states. They don't have any particular symmetry or anti-symmetry properties. Okay, another thing that you can do is you can use these tensor products recursively to add 3 or more angular momentas. And really what that means when I say we're adding 3 or more angular momenta, what we're saying is that we can find an orthobasis either for all of the m values of the individual angular momenta, or we can find a basis that is an eigenstate of the total angular momenta j squared and its m value. And then there's some way to work out what the coefficients are between those two basis sets of states. So the way you can do this is you just use the fact that you can already do pairs of them. So for example, if I have 3 of them, then I can combine first J1 plus J2. This is schematically, this is not supposed to be interpreted as an equation, but rather as a process. Okay, so I can get J12, which is the total of just those two, and then combine that with the third one to get the grand total angular momentum basis. So this can be quite complicated because you're going to use Clebsch-Gordon coefficients, and then you're going to use Clebsch-Gordon coefficients on top of that. But at least it's an algorithm that can be followed. Okay, and the total angular momentum basis means that you have eigenstates of j squared and j sub z. But one thing I want to emphasize is that when you do this, you are very likely to need redundancy labels. In fact, I should say you need additional redundancy labels, because all of the states that we've been talking about, we've been just writing down the angular momentum labels, but there could be other labels that, for example, label the radial quantum numbers. Like in the hydrogen atom, we had different radial wave functions. So when I say additional redundancy labels, I mean besides those, just things that are redundancy labels just even within the angular momentum part of the state. So it's easier to say what I mean there by doing some examples. So one example that you can do is just, what if you have 3 spin 1/2? Okay, an example of that would be in the lithium atom, for example. So if we take the tensor product of 3 spin 1/2, I can think of that as first taking the tensor product of the first two, which gives me a 1 plus 0. And then I'm going to take the tensor product of that with the remaining third spin. And we can do this with a distributive property. First, we have 1 tensor product 1/2, which is going to give 3/2 plus 1/2. And then I have spin 0, or angular momentum 0, with 1/2, which gives another 1/2. Okay, and so what's the meaning of that? It's that, well, first of all, let's count states on the left. So on the left, how many states are there? Each of the spin 1/2 has 2 states, and I'm taking their product. So I have 2 cubed equals 8 states total. And on the right over here, the meaning of this is that we can write down a total angular momentum basis labeled as follows. Okay, so the 3/2 tells us that there's going to be 3/2, 3/2, and there's going to be 3/2, 1/2, and there's going to be 3/2 minus 1/2, and there's going to be 3/2 minus 3/2. Okay, so that's 4 states. And they're basis states, so they're linearly independent, so we can really count them that way. And then I have, over here, I have 2 different angular momentum 1/2 things. So the basis for them, I can label like this. The total angular momentum is 1/2. The m component is 1/2. And then there's a number alpha, which runs from 1 to 2. And that number 1 to 2 just tells us which of these two things, which of these 2 angular momenta we're talking about. Okay, so there's that. And then there's 1/2 minus 1/2, again labeled by which one of the angular momentum 1/2 we're talking about, this one or that one. Okay, and so again, alpha the redundancy label can be 1 or 2. And so if we count how many of those there are 2 for the alphas. And then there's 1/2 or minus 1/2. So there's another factor of 2. This is for m equals 1/2 or minus 1/2. And so that's also 4 states. And so hooray, the counting works because 4 plus 4 is 8. And that matches with the number of states we started with here. Okay, so let's just do one more example of this sort of thing. Suppose I had 4 spin 1/2s. Okay, and one thing I want to emphasize with this example is it does not matter what order you choose to combine the angular momenta with. So I could do it this way. In fact, I will do it this way. Here are my 4 spin 1/2s that I'm taking the product of. I'm going to choose to combine these 2 first, and then I'm going to combine these 2, and then I'm going to combine the total. Now, however I do it, let's count the number of states we're going to expect first. There's 2 states for each spin 1/2, and there's 4 of them, so there's 2 to the 4th is 16 states. Okay, now if I combine the first 2, that gives me spin 1 and spin 0. And I'm tensor producting that with the 3rd and the 4th one, which also gives me spin 1 or angular momentum 1 and angular momentum 0. And then we distribute this. So when I do 1 tensor product 1, that gives 2 and 1 and 0. But then I can do this 1 with that 0, and I can do this 1 with that 0, and those each give 1. Those each give 1. And then there's finally the 0 with the 0, which of course gives 0. And so now if I just remove the parentheses and put these all in the same order, this is telling us that there are, let me write it on the next slide here. That's telling us that there are 2 and 1 and 1 and 1 and 2 angular momentum 0 components to this thing. Okay, and if we add these up, the number of states in an angular momentum 2 is 2 times 2 plus 1 is 5. Each one of the angular momentum 1s has 3 states. And there's only one angular momentum 0 state. So I get 5 plus 3 plus 3 plus 3 plus 1 plus 1, which by advanced methods turns out to be 16 again. And so everything works and it checks. So we did it one particular way. We could have also, for example, decided to first combine these 2 and then combine those 2 with this one, and then take the result of that and combine with these. But we would have gotten the same answer in the end for the total here. It would have given the same exact result for the allowed states. So one place this comes up a lot is when you're doing atomic physics. We'll see that for those of you who take Physics 661, which I hope you all will. But just as a preview, there's a code for how you write these things called spectroscopic notation. And this is applying to n spin 1/2 particles, and it's almost always electrons that we're talking about. So electrons have spin 1/2. And so the idea is what you do is you choose to first combine the spins. You don't have to do that, of course, but That's just what people do. And so you get a total spin that you get by combining all the n spins. But these things also have orbital angular momenta, and then you combine those separately. And that quantum number you call capital L. And then once you've combined all the spins together and all the orbital angular momentum together, then you combine those into the total, which is called J. Okay, and so that's giving you a basis of states, which you then write in the code where the superscript is 2s plus 1, the main number is L, and the subscript that goes in front is the J value. But then, just to make it more intimidating, you replace the L value by a letter. And then the letter you replace it by is S, P, D, F, and then after that it goes alphabetical, where S means 0, and P wave means 1, and D wave means 2, and F wave means 3, etc. Okay, so just for example, let's say you have a single electron. That's not a very complicated atom. Oh, I should say one thing about why this is useful. So it's not necessarily obvious that it's the best thing to do to first combine the spins and then combine the orbital and then get the total. And the reason this is actually useful is it turns out these are approximately Hamiltonian eigenstates. Then it turns out they're not exactly Hamiltonian eigenstates in this basis. And the reason for that is something called the fine structure, namely the spin-orbit coupling of the fine structure. But because they're close to Hamiltonian eigenstates, it's a good way to classify states. And then you can put in the fine structure, which turns out to mix them up a little bit, but in a very small and controlled way. So that works for sort of smaller atoms. When you get to really atoms that have a large number of electrons, then this starts to work less and less good. And then it turns out you have to do something else called JJ coupling, but we won't talk about that today. Okay, anyway, going back to a single electron, if I have a single electron, then my total spin, S, is just going to be 1/2. And so my pre-superscript here is always going to be 2 times 1/2 plus 1, which is 2. So the pre-superscript is always going to be 2 for a single electron. The orbital quantum number, L, can be anything, any integer. And then the J can be either L plus 1/2 or L minus 1/2. So the allowed spectroscopic notation states are 2s, that means that S wave means orbital angular momentum 0, and then the J has to be 1/2, or 2 P wave, and then I can have 1/2 or 3/2. Or for the D wave, which means according to the code orbital angular momentum 2, it can be 2 D 3/2 or 2 D 5/2, okay, or 2 F 5/2 or 2 F 7/2, etc. So a single electron is pretty easy to arrange these things into their spectroscopic notation, as we've just done. Let's talk about what happens if you have 2 identical spin 1/2 particles. So there's a new feature that I haven't told you yet, but you've probably heard of it. And that is the concept of Fermi statistics, which says if the particles are really identical and all electrons are the same so they're identical, then the state has to be anti-symmetric. That's a postulate of non-relativistic quantum mechanics. You can actually prove it as a theorem in relativistic quantum mechanics under the interchange. And so that's why it was useful for us to understand the symmetry and anti-symmetry properties when you combine angular momenta. So you can think of this, any wave function, as a tensor product of a spatial part. Let's say my two states for my two electrons are psi1 and psi2, if I just consider the spatial wave function. And then a spin part, where it's epsilon1 and epsilon2, where epsilon1 and epsilon2 are either up arrow or down arrow. And then what we can do is we can construct symmetric and anti-symmetric states for the different parts separately and then combine them. So first we can construct symmetric and anti-symmetric spatial kets. Okay, and so to do that, I can label them, A and B are the labels for the two electrons. Okay, and this is 1 over square root of 2. I'm going to write down just the only thing I can that is symmetric under interchanging them. Namely, I take the tensor product in one way, and then I exchange the labels and I add them together. Okay, and then the 1 over square root of 2 is just for normalization. So that's the symmetric combination. And then there's the anti-symmetric combination where I just put in a relative minus sign. So I'll just write here minus with the same two states. Okay, and then the rule of Fermi statistics up here tells us what's allowed for the total states. The total states have to be anti-symmetric. And so one way I can do that is I can combine the symmetric spatial state with the anti-symmetric spin state. So I'm going to write a column here that's spatial and spin. And so there's psi AB symmetric and 1 over root 2 up arrow, down arrow, minus down arrow, up arrow. Okay, and we recognize that as the spin 0 state. So that's saying if it's symmetric spatially, it has to be spin 0. And then I can do the anti-symmetric combination of the spatial state with any one of the symmetric spin states. So there's one. Here's another one. Okay, 1 over root 2 times spin up, spin down, plus spin down, spin up to make it symmetric. Or I can do them both spin down. That's also symmetric. But if I make it symmetric under spin and anti-symmetric under spatial, that also works. So these are the allowed states, and they have total spin equals 1. So here I'm writing the total spin. So in terms of spectroscopic notation, if the spatial states happen to be the same, in other words, psi A and psi B are the same, then I can't write down an anti-symmetric combination because the anti-symmetric combination up here would just vanish because of the minus sign. I'm subtracting the same thing from itself. So that means the only thing I can get is s equals 0, and so the superscript is 1. And so the allowed spectroscopic notations are S1, 1s0, 1p1, 1d2, 1f3, These are the allowed things for 2 electrons in the same spatial state. For different spatial states, then I can have both symmetric and anti-symmetric combinations. So if psi A is not psi B, then I can do this with spin 0, or I can do this with spin 1. And so I'm going to get all the same allowed things, but I'm going to get some additional combinations that have total spin 1, which means the pre-superscript is 3. So I'm going to get 3s1, 3p0, 3p1, 3p2, etc. Also, in addition to the ones that were allowed up here. Okay, so this spectroscopic notation is just a fancy way of saying what are the allowed combinations of different angular momenta allowed by Fermi statistics. That was for 2 electrons, and of course it gets more complicated when you try to fill out the whole periodic table of atoms with different numbers of electrons. And so that's, again, something that we will get into for those of you who take Physics 661. All right, so I actually went a little over time, which I apologize for, but that's the way things go this semester. I want to thank you all for sticking with the class, and I hope you've learned some good stuff. And again, thank you very much for sticking with it in tough times. And good luck on your final exam, which is due a week from today. All right, are there any questions I can answer?
Professor, I had some questions from the last homework assignment, and as well as some of the notes. You have time
Okay.
to go over them. I don't know if you want to keep recording or not.
Okay, let me just ask, are there any other questions or comments about today's lecture before we turn off the recording? All right, if not, I'll do that.